So moving on to the first problem. This problem asks us to find the Thevenin and Norton equivalent circuit. So let's run through our steps first. We're looking at this circuit and we see that one, there are no dependent sources. And there are none. So we shall move on to step 2, where we will zero out our sources. That's where we take the current source and we're going to turn it into a flipped out wire. So seeing here, we only have that one current source. So if we go and redraw the circuit, okay, and R3. We treat this as plus minus VOC. And now what we're going to do is treat VOC like it's a battery. So step 2, we'll find our R Thevenin. So looking at this, if we're treating this as a battery, some current will leave here, hit this point. Some will go down R3, some will come this way, some will come this way. Hits this point, and it has two options. It can either go this way where there's an open terminal, and we can't do that, so no current travels that way. So the current just continues on down through this R1 resistor. It meets back up to complete the current flow. Yeah. So our circuit, well, let's simplify it down. Since this clipped out wire is not doing anything for us, we can just effectively ignore it. And now what we'll do is we'll work this way to find our equivalents. So I'll see that these two are in series. So I'll write R series 1 will be R1 plus R2, which will be 1 plus 6 will give us 7 kiloohms. And real quickly, I'll redraw. So 7 R3 value. It's going to be 3 kiloohms, so R3. And we still have that VOC hanging out here with us. I'll see that these two are in parallel. So R parallel 1 will be 7 times 3 over 7 plus 3, which would be 21 over 10, which will give us 2.1 kiloohms. And if we redrew it one more time, it's 2.1. VOC, a little small there, but so we see that we only have one resistor and one source. So our equivalent is 2.1 kiloohms. Since we only have the one resistance, that'll be our R Thevenin. So this is one part. But we need two parts. We need to know either the Norton current or the voltage. So to do that, we need to now return return to OG circuit and find VThev or I Norton. Okay. And looking at the circuit, there's a couple things we have going on here. This is the original circuit, and this is open. It means that no current will travel through the open wire. Okay. But despite the fact that there's no current going through this wire, it's still got voltage in it. So the voltage there will be the same as the voltage there, same as voltage there, same as voltage there. So these 2 points have the same amount of voltage. And same deal down here. So those 2 points have the same voltage. So if I can find the voltage from here to there, I find the voltage VOC. And looking at this, we see that that would be the voltage drop across this R3. So if we can find that voltage drop, we find VOC. We can find VThev. Okay. So if we look at that original circuit, let's see what we got. We know 24 milliamps comes up through this way. We see that some will go down this way and some will go down this way. So if we can find this current, the current that goes through here will be the same. The current that goes through there, goes through there, and goes through there. None goes down there, none goes down there. So by doing a simple current division, so I of S R1, R2, and R3. Okay. So there and there. We know this is I of S. For funsies, I'll call this I2. So doing a current division requires that we have a few pieces of information. So R parallel over the R total resistance of the branch. So it's going to be this one and that one. So we're going to multiply it by our source current that's being broken up, the current that's being broken up. So now what we're going to do is work that way to find our resistance values. And there's a little spotty there. Okay, so seeing right here, for sake of simplicity, we can see that these two are going to be in series. Okay. And then once I combine these in series, these two will be in parallel. So we'll look at R series, R2 plus R3, and that will give us 1 plus 3, will give us 4 kilo ohms. Then our R parallel give us R1 times the R series value, or R1 plus the R series value. Go ahead and punch that value in real quick. Okay. This will give us 2.4. So 2.4 kilo ohms. So there's our R parallel value. So if we go plug this in, we'll get current 1, which gives us 2.4 over. So R2 plus R3, so 1 plus 3 times 24 milliamps. Divide that by 4. Divide by 24. That'll give us 14.4 milliamps for I1. now to find the voltage across R3. So the voltage 3 should be IR. And I realize here that should be I2. So apologies for that. I2. So we're solving for that current. Okay. This will be I2 times R3. So I2, which we found was 14.4 milliamps. And then our R3 is 3 kilo ohms. So this will multiply to give us 43.2 volts. This is voltage 3. And we found that voltage 3 is the same as voltage VOC. So voltage 3 is equal to voltage VOC, which is equal to VThev. So 43.2 volts is VThev. Okay. Then if we just go and drop those into our circuits, remember Thevenin's going to be in series. So Rthev 2.1 kilo ohms, VThev 43.2 volts, then plus minus VOC. Then if we want to find I Norton, like we said, is VThev over Rthev. And this will give us 20.57 milliamps for I Norton. That's the general flow. So you're going to work. Initially, you're going to have to work from left to right, and then from right to left. All right. Now, something important for these Thevenin problems, and this will happen, I can guarantee it, a load resistance. So what is a load resistance? What a load resistance is that, okay, so instead of us having these open terminals here and putting just this wire, what if now we went and added a resistance and we call that RL? Well, that changes our problem now a little bit. So let's go and take a look at this. So first, let's see step 1. There's no dependent sources. Good. So we'll zero out. 4, 0 out. Pardon me. So here we only have a battery, and our battery is going to turn into just a wire. So if we redraw that, we'll get here and here. This will be R1, be R3, it'll be R2. And we haven't dropped that load resistance in yet, so I'm just going to put VOC. Typically, you'll add the load resistance at the very end. So we'll have VOC, and we're going to work that way towards the battery. So if I slid this one over, see that these two are in parallel. So if I write that out, R parallel will be R1 times R2 over R1 plus R2. So 10 times 100, 10 plus 100. Give us 9.09 ohms for R parallel all the way down. R parallel, here's R3. Go C. Then I see these two in series. So I can do, come on, R series, R parallel plus R3, 9.09 plus 80, so 89.09 ohms for R series. And since we can see here that after we combine these, there will only be one resistor, our equivalent 89.09 ohms, which is our R Thevenin. So we have that value. But now what we need to do is find the voltage across from here to there. Okay. Looking at the original circuit, you can see current will lead through here, pass through this resistor, pass through that way, come down through here, here. It'll bypass right there because it's an open terminal, so that R3 doesn't actually do anything for us. Skips over this open terminal as well, and then loops itself back that way. Okay, so you can see that there's a loop. So we have a couple options here, because even though no current's running through here, we still said that the voltage at this point, same as the voltage at that point, and the same at the bottom as well. So if we can find the voltage across this resistor, R2 resistor, then we can find the V Thevenin. So we have two options. We can either do a let's just do a voltage division. It'll be a little bit easier for us since it doesn't require us to solve for this current value here. Because this is one single loop, we can do a KVL on it. R2, R1, and then VS. Okay. So to do a KVL, what we're going to do is we'll do, let me grab this. We'll walk our loop this way. We'll just assign a, we can assign whatever terminal we hit that sign, or we can just go ahead and do the voltage division because we can just see clearly that it's going to be split up between these two resistors. So if I want to find voltage across R2, what I'll need to do is do R2 over R series times VS. So VR2 is equal to R2, and R2 we said was 100. R series, you can see it's R1 plus R2, so 10 plus 100. V of S we have is 16 volts. So punching that in, will give us 14.54 volts for VR2. And we said that that is equal to V Thevenin. So there we are. Okay. So let's go drop all this into a Thevenin circuit. Plus minus VThev. Get those out of the way. This is RThev and VThev. Okay. But now we're introducing that wire and the load resistor. Okay. So now we're changing things. We changed the resistance of the circuit itself. Okay. And because this loop is there, with this RL, I'm going to call this a current I of L, so I load. So I of load, if we want to find I of load will be V Thevenin for R total resistance. Okay. So we know that this is 14.54 volts. And we've got 89.09 ohms from the R Thevenin. And we said that our R load, so R load is going to be 20 ohms. Okay. So 20 ohms. Let's go ahead and punch that in real quick. This will give us 0.133 amps for I load. Okay. The reason why we're doing all this, because we need two pieces of information. We're looking for the power absorbed by this load. So if we're looking for the power is equal to VI. Well, we now found I. Great. But we still don't have V. But because we now found I, we can find V. So V of the load equal to I of load times the resistance of the load, 0.133 amps times 20 ohms. 20 ohms. So 2.67 volts. Okay. So 2.67 volts is our V of load. So if we take those two, plug them in, we will get 0.354 watts. So P of load. Looks like a 2 load. Okay. So there we are. So we have to essentially do two separate problems. Whenever they do the load, it adds an additional element, and it takes a little bit longer. But same process, going from left to right, and then going from right to left, finding R Thevenin, finding V Thevenin, and then finding power, current, or voltage, whatever they're asking for. Quick note here, if you want to solve it using Norton, A-OK too. I'll just do that for you real quick. So I Norton is going to be equal to the VThev over RThev. .163 amps. Okay. So it's I Norton. This is R Thevenin. And when you introduce that load now, R load, now the current is going to be split. So I Norton will split up into those two branches. Okay, and I'll leave this to you to solve for the parallel values. But what you'll do is to find our I of L, the same current that we found earlier. So I of L will be the R parallel over RL times I Norton, which gives us 0.133 amps. Our parallel value is the 16.33 ohms. Okay. So therefore, V of L, I of L, R of L, give you the 2.67 volts. Okay, so same process either way. So the power will still end up being 0.354 watts. So it's your world. Do whatever you want to find these power values. You can either do the Norton or the Thevenin. It's really up to you. Let's move on to source transformation. Okay, so source transformation is neat. It essentially helps us by letting us bypass longer methods of analysis. So like the nodal analysis, the mesh loop analysis, things like that. But it has to meet certain criteria. So like we said before, it has to be the parallel and the series value from the concepts. You have to have a current source in parallel with the resistor, and then you have to have the resistance in series with the battery. So if we just write that out. Okay, just a quick refresher. So we gotta have this whole scenario. Okay. Now here's a key concept. So we did this at the very beginning of the semester. So if I have all of my sources as current sources, okay, say I have 2 up and then 2 up, I can add them together to give me one current source, essentially combine them together, okay? But this only works in pure parallel. Okay, I'm stressing that real hard right there. Okay, you'll see what I mean by pure parallel in just one second. But let's look at this concept real quick. So if I have 2 going down, and I've got 4 going up, add them together, and I'll take the remainder to 2 going up. Okay, so this is very powerful, but everything has to be in parallel. Okay, so nothing in between the branches. Okay, so what we're going to do is looking at this problem here. They want us to find this current, and this current is I1. They defined it for us. Okay, so I1's going down that way. They gave us all these values. So you could do a nodal analysis problem where you could drop a ground here and then go right there and then solve for that value and then solve for that value. But that'll take a lot of time. So if they say use a certain method, use that method. It's probably a reason for it. Okay. So source transformation, what I want to do is end up combining these current sources down. So here, so you have a resistance in series, a battery in series with this resistance. So I can redraw this circuit. It's 2 going up. That's 10. That's 10. This is 5. And then now, since I'm turning this into a current source, I'm going to pull that 10 down. But let's find this I value. So this I will be the voltage. Wow, it's acting a little buggy right now. So voltage over the resistance. So those two values that we pulled. So 10 volts over 10 kilo ohms plus 1 milliamp. Okay. So this value here is 1 milliamp. But let's keep looking. So great, now I've got two current sources. But this isn't in parallel. The entire circuit isn't in pure parallel. Because that resistor right there, okay, that's blocking this entire thing from being in parallel. Because this now absorbs a little bit and prevents all of these from having the same voltage drop across them. So with that in mind, I see that these two are in parallel though. So I can combine those two. So I can say R parallel 1 will be 10 times 10 over 10 plus 10. And that will give me 100 over 20. Give me 5. Okay. And I'll redraw the circuit. 10. There's 2. 5 at the top. Then 5 right here. I still have 1 milliamp right here. It's acting a little buggy when I try to write on the sides of the screen. Okay. But I still have an issue because this thing still isn't in pure parallel because of that resistance again. But I can see that if I was to take that resistance and pull it up to that wire, then I could combine these two resistors in series. So let's turn this into a battery. Because turning it into a battery will pull that 5 to that wire. Okay, that's 10. That's 2 still. Okay, but now this voltage is going to change. Voltage is the I times R. So I, so this is the 1 milliamp. The resistance is 5 kilo ohms. So it gives us 5 volts. So now we have 5 volts instead. Okay. So we started with a 10 volt battery and went to a 5 volt battery. Then we see that these two are in series. So let's combine those down. So our series, 5 plus 5, will give us 10. Okay. Plus minus 10, 2, 10, this is 5 volts. Okay. We're still not quite there yet, because now that one. But we could turn it into pure parallel by just converting it into the current source. 10, 2, and then pulling that 10 down. This current source, I, is equal to V over R, 5 volts over 10 kilo ohms, 0.5 milliamps. So 0.5 milliamps. Okay. Now let's look at it. Now this entire thing is in pure parallel because there's nothing blocking these branches in between. Okay. And I see I've got 2 going up and then 5 going up, or 0.5 going up. So I'll redraw it. to 2.5 milliamps. Okay. This is 10, and this is 10. And notice I didn't change this at all from the very beginning. So, like, this bit is still that bit. So that hasn't been altered. So this current is still that I1 value. Okay. So we know that 2.5 comes out this way. We know some will go that way. We know some will go that way. So let's do a current division to find I1. Okay. Current division to find I1. We'll need R parallel over R. This is the 10 ohm. We're going to split it up from the source current. So R parallel will be 10 times 10 over 10 plus 10, which will give us 5. 100 over 20 give us 5 again. So this will be 5 over 10 times 2.5 milliamps. So I of 1 is 1.25 milliamps. Okay. There we go. And for those of you who are have kind of done a few of these and seen, like, got a good bit of practice with it, you can kind of see that this is 10 and this is 10. So the current is indifferent on which way it sends more current when it breaks it up. So equal amounts will be sent down both branches. Okay. All right. So that's the first 3 problems. I'll see you in the next video for the next 3 problems.